In this video, I want to talk about one more type of sampling distribution. In fact, two types, but they're kind of the same. It's the one sample and the two sample version of the same thing. And they are population proportion distributions. And these come into play when we have a category and we're interested in how many of a population satisfy being in this category. So it's kind of like a yes or no question. So it's a binary category. Is it in the category? Is it not? That's all we care about. And a good question is, well, we can't sample everybody in a population usually. So how can we estimate what the actual proportion of our population satisfying being in this category is? What's the proportion of the population in our category? So that's what we'll work on in the first few slides here. I'll set up some notation, and then we'll talk about what this distribution looks like, and it turns out it's going to be nice and normal for us. And then we'll do an example, and we'll talk about a couple of things as well. So here's some notation. So when we're talking about the true proportion, we use this lowercase p here. So this is akin, you're thinking of this like mu, like a population mean. But because it's a proportion, we just use the letter p instead. And the standard deviation of the population, we still use sigma for that. Now, just like with other sampling distributions, the idea is we're going to take a sample of n things, and we are going to estimate our parameter by our sample. So we're going to estimate the true population proportion by taking a sample of, say, n observations, and we can calculate this sample proportion here, just from our sample. So this is the sample proportion. We call it p hat. And you're thinking this is akin to x bar when we're talking about sampling distributions of means. And basically, it's how many successes there are out of the total number. It's a lot like probability. In fact, this is in some senses related a lot to probability and the binomial distribution a whole bunch, because it is talking about basically probability of success or proportion of successes. Now, so that's akin to our x bar. What's akin to our s? Well, it can be shown that our standard error here, which we usually write as sigma p hat, but we can just say standard error here, is, well, I have a little typo. I didn't finish this formula. Let me finish this off. It's actually this over n, and then you take the square root of everything. And just note here that 1 minus p, a lot of times in books, you might see the letter q representing 1 minus p. It's just the proportion of quote-unquote failures in your sample. And also what's really nice is that if n is large enough, and we'll talk about that on the next slide, we can use our sample proportion to take the place of the population proportion. And just like before, instead of 1 minus p hat, the sample proportion of failures, you might see q hat instead. And again, I'm missing this denominator of n here. So here is our formula for the standard error of our sampling distribution, as long as n is large. And we'll talk about what large means on the next slide here. And the shape of this distribution is very nice as long as n is large. And by large, that really depends on what your p is here, what your population proportion is here. So for this class, we say n is large when n times p is greater than or equal to 15, and n times q, or n times 1 minus p, is greater than or equal to 15. And the reason that is, we talked a little bit about this when we were talking about the binomial distribution, but if n is small, if one of these two things fails, what that means is we get kind of a distribution that butts up against either 0 or 100% too much, and it doesn't look particularly normal. So if n times p is too small here, then we get a distribution that looks like that. And if n times q is too small, we get something that butts up against 100%. It's too skewed for us, and it doesn't look particularly normal. But if n is nice and large, then our distribution is going to look fairly normal, which is great. And for our purposes, 15 is going to be our cutoff for normal. So that's fantastic. We know our sampling distribution is going to be approximately normal. We have a standard error, so we can start using our normal table to calculate probabilities and to find confidence intervals and whatever we like. So that's fantastic. And let's look at an example on the next slide here. So here we have a very familiar scenario. If you ever watch the news when an election is happening, there's polls that always come out. And they say, we've polled so many Nova Scotians, and we've said that, so many of them would vote for a particular political party, and then they talk about some numbers. So we're going to kind of recreate basically how they come up with these numbers and what they mean. So let's say in our sample, there was a sample size of 350. We took 350 Nova Scotians. We asked them, would you vote for the Progressive Conservative Party in the next provincial election? And 105 of them said they would. So that is our sample. Our population is all voters and all potential voters in Nova Scotia. Okay? But of course we can't ask all potential voters. That's an election. So if we're a polling firm, we can only ask a small subset of that. So what's our sample proportion? Well, our sample proportion here is just the number of successes. So our event is voting for the PC party in the next election. 105 people would fit into that category out of our 350. So our proportion is 105 out of 350. And if you calculate that on a calculator or whatever, you find that's exactly 0.3. So that's our sample proportion. 30%, remember 0.3 is around, or is exactly equal to, 30%. So 30% of the voters we asked would vote for the Progressive Conservatives in the next provincial election. But remember, that's not all Nova Scotians. So we need a confidence interval to account for some variability there. So we're asked to construct a 95% confidence interval for the true proportion of Progressive Conservative voters in Nova Scotia. And before we do that, we should check that we're allowed to kind of use a normal distribution to approximate our sampling distribution. So let's check if n is large. We should always do this before we do anything with these proportional distributions. So let's do n times p first. So n times p is 350 times 0.3. Well, we know exactly what that is. That's the number of successes, is 105. And we're using p hat here instead of p because we don't know what the true proportion is. But our sample size is going to be large enough that it's not going to be an issue. And let's calculate n times q hat. So that's 350. And remember, q hat, that's just another name for 1 minus p hat. So the proportion of quote-unquote failures. So it's the number that would not vote for the Progressive Conservatives next election. That's 350 times 0.7, the rest of them, if you will. And if you do this, you get 245. Really, another way to think about this check, this n times p hat and n times q hat, is there's not less than 15 observations in each category, either success or failure. Here there are 105 successes and 245 failures, so our sample size is definitely big enough so that our sampling distribution will be approximately normal. Okay, let's move on and let's calculate this confidence interval. Okay, so remember, we want to construct a 95% confidence interval. So confidence interval where the probability that the true proportion, the population proportion, is inside of this interval is 95%. And remember from the previous slide, we had our sample proportion was 0.3. So 30% of our sample would vote for the Progressive Conservatives. And we want a 95% confidence interval. So remember, we have our sample distribution, which has the same mean as the population distribution, just like for sample distributions of means. This also holds, which is great. And maybe I'll write that as well, the mean proportion in our sampling distribution. So I'll write that maybe as, what will I write it as? I guess p hat is the same thing as the true proportion, so that's great. So we want a 95% confidence interval, so we need to figure out the middle 95% of our data, just like confidence intervals in means. Same idea works. There's 2.5% of our data outside of that, so we need to find z of 0.025. Sorry, 0.025, 2.5%. And if we look in our table, we get 1.96. So 1.96 standard errors from the mean. And that's going to be really important to us when we construct our confidence interval. Of course it is. Our standard error for this sampling distribution, well, that's just p hat times q hat over n. Remember, our sample is large enough that these guys are really close to the true values, which is great. So we get p times q over n, and then take the square root. And if you do that calculation, you get 0.0245. Okay, we have everything we need to be able to build our confidence interval. So our 95% confidence interval is going to be our sample proportion plus minus z alpha over 2 times our standard error. And just as a reminder, this guy here is called our margin of error. Okay, so what is this going to be? This is going to be 0.3 plus or minus 1.96 standard errors. And we calculate our standard error to be 0.0245. And our margin of error, if you calculate that, is 0.0478, we'll say. So, writing an interval notation, our confidence interval is going to be 0.252222 and 0.3478. So we are happy, and how happy are we? We're 95% happy. We're 95% confident that the true proportion of Nova Scotians that will vote for the Progressive Conservatives in the next election is between 25.22% and 34.78%. And if you read this in news articles, or if you hear it on the news or polls, you'd probably hear it reported as, well, the PCs are polling at 30% plus or minus 4.78%. And then to say it's a 95% confidence interval, they'll say it's 19 times out of 20. Since 19 times out of 20 is 95%. So that is our confidence interval for the true proportion of PC voters for the next election. A few notes here. So, the first one we're not going to deal with in this course, but if you have a small sample size, if n is small, and what really, remember, that means it's a kind of a combination of looking at n times p and n times q. If these are small, so n times p is less than 15, or I should say or, not and, or n times q is less than 15. If in your sample there are fewer than 15 successes or fewer than 15 failures, then there is a way of dealing with this. It's called Wilson's adjustment for estimating the true population proportion. But we're not going to cover that in this course. Okay, the second thing is an error that I find a lot of students make. When they're reading a problem, they might see a percentage and are thinking, oh, there's a percentage involved, it must be a population proportion question. But that's not necessarily true. Let me give you two examples. One, which is a non-example, where it's not a population proportion, and the other one that is, so you can start to see the difference. So here's a non-example. Let's say somebody's interested in the mean percentage that an oil tank is filled of a household that has oil for heat. So they took a sample of 55 oil tanks, and they found that the average amount the oil tank was filled was 40%, with a standard deviation of 9.2%. So here, there's not two categories involved, either a success or a failure. It is a measurement of something. So this is actually a measurement of a value, not whether you're in a category or not. So this is not a proportional distribution, not proportion. It is a measurement. But if you're reading here, and it says a sample of 108 students found that 53% of them have missed at least one class due to illness, now you're talking about being in a category. Did you miss one class due to illness? And if the answer is yes, then you're a success. You're part of this 53%. So this is a proportion. So it's a good idea, if you're ever unsure, ask yourself, what would one observation look like? If it's just a yes or a no, or in or out, then it is indeed a proportion. And if one observation looks like it's a number or a percentage or something like that, then it's not a proportion. So that's a good way to distinguish between just percentages appearing in a question and being actually proportions.